have the video content with you if you want to once again listen to the complete lecture. Okay, so this chapter, basically there are two parts. First part talks about what is the magnetic effect due to various conditions. That is magnetic effect due to a current element, magnetic effect due to a straight current carrying conductor, magnetic effect due to circular current carrying conductor, central point, axial point, magnetic field due to a solenoid. So this is all about the first part of the chapter. The first part talks only about finding magnetic fields. Second part talks only about force and torque acting on the current carrying conductor kept in a magnetic field. So how a charge behaves when it is moving in a magnetic field, how a current carrying conductor behaves if it is kept in a magnetic field, how two parallel current carrying conductor behaves when they are kept close to each other, how a coil behaves when it is kept in the magnetic field, and all these things are in the second part. So have the clarity about what you're going to learn. First part, you're going to learn about finding magnetic fields. Second part, you're going to learn about finding forces and torques. So let us start with the first topic in this chapter. So first topic in this chapter is Biot-Savart law, if you remember. So Biot-Savart law, why it is used? It is used to find what? It is used to find magnetic field due to a current element. Remember that. It is used to find magnetic field due to current element. What is the meaning of the word current element? Current element is the part of the wire which carries the same current as carried by the whole wire. So that small, suppose I'm having a wire, it is taking current I, then a small part of the wire is called as DL, current element, which carries the same current I. And if I want to find R distance away from it, what is the value of magnetic field? Since I am taking a small portion, I'll have a small magnetic field dB. So I can easily find the value of dB for this DL, and that will become equal to mu naught by 4 pi I dl sine theta by r square. This is the value of magnetic field due to a current element. So magnetic field due to a current element is this much. This is scalar representation of magnetic field. If you want to find the vector representation, never forget dB vector is equal to mu naught by 4 pi I dl vector cross r vector by r cube. Sometimes you will forget this cube sign. If you write here square, it is wrong. So if you are writing in vector form, it is dl vector cross r vector by r cube. Moreover, here I will put a r cap direction. R cap is the direction of magnetic field, which always is in the direction perpendicular to plane consisting dl and r. So whichever plane is having dl and r, perpendicular to that plane only the magnetic field will act. For example, in this case, the magnetic field at this point can either be into the plane or out of the plane. If you see into or out, they are perpendicular to this dl and r. dl r is in this plane of the board. But magnetic field cannot be like this. It will be either like this towards you or it will be into the board. That's how the magnetic field is. Perpendicular to the plane consisting dl and r. Moreover, what is theta here? Theta is the angle between dl and r. This is only theta. Angle between current element and this line joining current element in magnetic field, that angle is called as theta. I hope you're understanding this. Then we have magnetic field due to straight current carrying conductor. For a straight current carrying conductor, if I am going r distance away from it, then the value of magnetic field is mu naught I by 2 pi r. See, I know that this is just one condition, but this is enough for you. If I am teaching the competitive class, then I will say there are three formula. Mu naught I into sine theta 1 plus sine theta 2, like that I will tell some formula, but not required for you, because this derivation is not there in your syllabus. But I am telling you about this because some place we will use it. So always remember, if you are having a current carrying conductor having current flowing I through it, r distance away from it, magnetic field is mu naught I by 2 pi r. Same way, if you have a circular current carrying conductor, at its center, the magnetic field value is mu naught I divided by 2r. This derivation I have done in the class. How did I derive it? I took a current element. Current element, if you see, the direction is perpendicular to the radius. So theta is 90 degree here. Put here dB is equal to mu naught by 4 pi I dl sine 90 by r square. dl will become, if you integrate full, it will become 2 pi r. When you put in the equation, you are going to finally get b is equal to mu naught I by 2r. Simple derivation. Very simple. But remember that mu naught I by 2r is for the complete circle. That is for 2 pi radians, 360 degrees. If you have a given angle that is for theta radians, then the formula becomes theta radians. The formula becomes b is equal to mu naught I theta by 4 pi r. If you remember the formula. This formula is used to find the magnetic field due to a circular current carrying conductor for some theta radians. For example, if you have a question where you have like this is given as some 60 degrees. Now this part of the conductor, how much magnetic field produces at this point, let the point be B, is given by mu naught I theta by 4 pi r. Remember that. So here r will be this length. Same way for this length, the value of magnetic field will be mu naught I theta by 4 pi r. Let this be r by 2, whatever it may be. You can find the value of magnetic field. Difference is, if the current is flowing in this direction, the direction of magnetic field by this part will be into the plane, and by this part will be out of the plane. You have to subtract both to get the net magnetic field. Remember that. See, those who are new to this, if you want to find direction of magnetic field, you can use right hand rule. If your fingers are representing direction of current, then thumb will give direction of magnetic field. And if thumb is giving direction of current, 4 fingers will give direction of magnetic field. Very simple. So suppose I am having a straight current carrying conductor. I am asking you here, what is the direction of magnetic field? You will keep your thumb on the current direction. The 4 fingers will go into the plane. You will say into the plane. If I ask you left side, your 4 fingers are trying to come out of the plane. You will say out of the plane. When I have circular current carrying conductor and current is in the clockwise direction, and if I ask you what is the direction of magnetic field in the center, then I will say it is into the plane, because I am putting my fingers in the direction of current, my thumb is pointing into the plane. So that's how we find direction of magnetic field. So in the case, if your thumb is giving current, 4 fingers will give magnetic field. If 4 fingers is giving current, thumb will give magnetic field. You're realizing that, right? So if I'm having an anti-clockwise direction current flowing in a coil, then automatically I am going to have out of the plane magnetic field in the center. So here, one part the magnetic field is into the plane, one part magnetic field is out of the plane. So B1 minus B2 will give you net B. Expect this kind of questions to come. Or the questions like semicircular arc, that is more simpler. So theta will become equal to pi radians. So if you put pi here, mu naught into I into pi divided by 4 pi r, pi gets cancelled. Obviously mu naught I by 4r is the magnetic field due to a semicircular arc at the center. One more way of thinking is mu naught I by 2r is for the complete circle. Half circle will be mu naught I by 4r. Half of that. Layman's way of thinking. But technically this is the reason for that. I hope you're understanding. Then in the class, I have spent a good amount of time in teaching you what is the magnetic field due to a circular current carrying conductor at the axial point. Very, very important. It will definitely come in the school exams, where you have circular current carrying conductor and axial distance away, suppose r distance away, they are finding the magnetic field value. So if it is r distance away and suppose radius is, or I'm taking radius is r, a distance away, whatever it may be, a distance away, radius is the r. Then the formula will become equal to, at this point B will be mu naught I r square by 2 into a square plus r square power 3 by 2. This is the magnetic field value for axial point, which is lying a distance away from the center of the current carrying circular conductor. Are you getting my point? This derivation is very important. I have taught in the class. If you want to re-look into it, you can see the video, you will once again understand it. What I'll do, I'll take a small current element in the top. I'll make directions of magnetic field. I will take small portion in the bottom. I'll find direction of magnetic field, and then I will resolve it. I'll get this expression. It is important for the examination. Mu naught I r square by 2 into a square plus r square power 3 by 2. And once again, by using our right hand rule, we can find direction of magnetic field. If it is taking anti-clockwise current, towards this side. Clockwise current, towards that side. Now, based upon this, there are so many questions that can come in the examination. For example, one coil here, another coil here, having different radius and this thing, current. And then they may ask you to find what is the net magnetic field somewhere, maybe somewhere here, or somewhere here, or somewhere here, or somewhere here. Anywhere they may ask you. Apply common sense and solve. Suppose if they ask you to find what is the net magnetic field at this point number 1. Then this, suppose here the current is clockwise, here the current is anti-clockwise. Here the current is I1, here the current is I2. And the distance between them is suppose something D. Then if you find at the point number 1, this circular current carrying conductor, at its center, the magnetic field will be mu naught I by 2R. And at this point, this coil will be at an axial distance D away. So here net magnetic field will be mu naught I by 2R, mu naught I1 by 2R plus mu naught I, this suppose the radius is R1 here and it is R2 here. So mu naught I R2 square by 2 into R2 square plus D square power 3 by 2. Are you getting what I am trying to say? So like that some questions may come. Or they may ask you to find, suppose here, let the point be 2. Second point. At second one, what will happen? This coil, axial. This coil, axial. So for both you will use axial formula. Difference may be the direction. So how to find direction? See, this is clockwise. If it is clockwise, magnetic field will be in this direction. If it is anti-clockwise, in this direction. Are you getting? Be very careful about this. If you are going to find the magnetic field due to circular current carrying conductor, like this kind of questions may come, be very careful about the magnetic field direction. Very famous question in the examination is this one. Expected to come in the school exams. Very commonly comes. So once again, here what will happen? One coil will have magnetic field maybe like this. One may have like this. Or one may have, but definitely they will be perpendicular only. It can be like this, or it can be like this, or it can be like this, whatever it may be, but magnetic fields will be definitely perpendicular. Because it may, for this coil, it may be like either here or here. For this coil, it will be either up or down. So these two are going to be always perpendicular. And if they are going to be perpendicular, the net magnetic field will be B1 square plus B2 square plus 2B1 B2 cos 90, that is 0. So root over B1 square plus B2 square. B1 you can find mu naught I by 2R. B2 you can find mu naught I by 2R. Solve, get the answer. This kind of questions are also very common. Another question that I have seen in the board exam is like this. One coil like this, another coil like this. They are finding magnetic field here. So for this coil, again axial distance. For this coil, axial distance. Find directions properly. Find the net magnetic field. B1 square plus B2 square plus 2B1 B2 cos 90. These kind of questions are coming from magnetic field due to circular current carrying conductor at central point or at axial point. Three formula actually. Mu naught I by 2R, mu naught I R square by 2 into A square plus R square power 3 by 2, or mu naught I theta by 4 pi R. These are the formula that are used to find the magnetic field at various points. Then comes Ampere's circuital law. Ampere's circuital law is used to find the magnetic field due to any current carrying conductor by drawing an Amperian loop. What is Amperian loop? Amperian loop is an imaginary loop which is used to enclose the current carrying conductor. Right? For example, if I am having a current carrying conductor, if I am drawing a loop, imaginary loop that is enclosing it, this loop will be called as Amperian loop. Amperian loop. So what Ampere's circuital law says, it says that integral of B dot dl is equal to mu naught times net current enclosed. This is the expression for Ampere's circuital law. Integral of B dot dl is equal to mu naught times net current enclosed. And by this, you can even derive mu naught I by 2R, 2 pi R actually. For a straight current carrying conductor, R distance away from it, if you draw the Amperian loop, then it will become B dot dl is equal to mu naught I net. Current carried is I. Integration of dl will become 2 pi R. send 2 pi r there, you will get mu naught I by 2 pi r. Sometimes they may ask you, using Ampere circuital law, derive the magnetic field due to straight current carrying conductor. Easily you can derive. By Ampere circuital law, we have even derived, not in the syllabus it is there, but for a solenoid, what is the magnetic field inside? That value is B is equal to mu naught Ni. What is N here? N is number of turns per unit length. Never forget that. Number of turns per unit length is N, small n, and magnetic field inside solenoid is mu naught Ni. What you should remember is, magnetic field inside the solenoid is uniform. Always same at all the points except the ends. At ends, the magnetic field is half. But anywhere inside solenoid, the magnetic field is same. So the graph also, if you want to draw for this, half, then maximum, once again half. That's how the graph will be. So graph will be maximum and same for the inside condition, and when you come outside the solenoid, the magnetic field becomes half of the maximum value. That's how the magnetic field due to a solenoid is. This was one part of the chapter. Next part of the chapter is talking about the forces acting. First thing in this is how a moving charge behaves in a magnetic field. I hope everybody knows that static charge experiences no force in magnetic field. The reason is, static charge does not produce any electricity, and electricity is not there, magnetic field cannot be there. Magnetic field is not there, how it will interact with magnetic field? So if you have existing magnetic field, and only if you have a moving charge in existing magnetic field, if I am having a moving charge, this moving charge will experience a force, and that force formula is QVB sine theta, Lorentz force, QVB sine theta, where theta is the angle made between its velocity and magnetic field. For example, here magnetic field is into the plane, velocity is towards the right, angle between them is 90 degree. I hope you are understanding. So angle theta is the angle between the velocity and the magnetic field vector. That will always be depending upon the angle. It will not always be 90 degree. It can be any other angle also. We have understood that if it is entering in 90 degree, that is normally, then you are going to have radius formula as mv by qb, time period formula as 2 pi m by qb, and frequency formula as qb by 2 pi m. These are the formula for radius, time period, and frequency when a charge enters the magnetic field perpendicular to it. Okay, if a charge is entering magnetic field perpendicular, then radius is this much, time period is this, and frequency is this. Apart from that, if the charge enters the magnetic field making some angle theta, magnetic field is this, and charge is not entering perpendicular, it is entering making some angle theta with the magnetic field, then the velocity will get dissolved in two components. This will become v cos theta, this will become v sin theta. Now you can understand that v sin theta is responsible for circular motion, v cos theta is responsible for horizontal motion. Combinedly, it will give an effect of spiral path, because v cos theta is pushing it front, v sin theta is making circular path. Circular path, horizontal path, it is getting a net motion in spiral direction. And what is the radius of it? mv sin theta by qb, because mv sin theta is only responsible for circular motion. What will be time period and frequency? It will remain same, because it is independent of the velocity. But new thing will come, pitch. Pitch means between two circular turns, what is the distance? Pitch. And what will be pitch formula? Time period multiplied by velocity, which will become equal to 2 pi mv cos theta by qb. Because v cos theta is the velocity in horizontal direction, and 2 pi m by qb is the time period. So when you multiply time period with velocity, what do you get? Pitch, distance you get, pitch. It is the horizontal distance. So if the charged particle enters perpendicular to magnetic field, it starts taking circular path. if charge enters making an angle theta with the magnetic field, it starts taking spiral path. Then we have learnt about how how a current carrying conductor behaves in magnetic field. This also I have derived in class. Derivation is very important. Please learn derivation. That is, if you have a current carrying conductor kept in a magnetic field, what is the force acting on it? And the answer is, force acting on it is ILB sine theta, isn't it? You remember this? ILB sine theta. It is the force on a current carrying conductor kept in a magnetic field. And then we have learned what happens if two parallel conductors are kept near to each other, no magnetic field. But since you have two conductors carrying current I1 and I2, they will be attracting each other by a force. That force value is mu naught I1 I2 L by 2 pi d. You remember this? Very important. D is the distance between them. This is the formula for force between two parallel current carrying conductors. Now, how it is acting, that also I have taught to you in the other class. I told you, by this current, there is a magnetic field in this direction into the plane. Magnetic field is there, current is there, ILB force will act on it. Same way, this is producing magnetic field like this out of the plane. Out of the plane magnetic field, current, it will get a force. Direction of force given by what? Direction of force is given by Fleming's left hand rule. Never forget that. Which says that if first finger is giving magnetic field, middle finger is giving direction of current, then thumb is giving direction of force. So by this you can find what is the direction of force. Whether force is acting upward, downward, you can easily find by that. So if you find the force direction, it will come as attractive in this case. And if there are two wires taking the current in opposite direction, they will be repelling each other, the same force. So two parallel current carrying conductors are attracting each other. If they are carrying current in same direction, they repel each other when they are carrying current in opposite direction. The magnitude of force, however, remains the same, which is mu naught I1 I2 L by 2 pi d. Based upon this, how is the question coming? Question is coming, the most famous question is like this. There is a coil carrying some current, and then we have a current carrying conductor. Suppose they have some distance given here, 1 meter, and they have given me 2 meter by 2 meter square. Then they may ask you, what is the net force of attraction or repulsion on this coil? You understand that these two are in same direction, they will attract. These two are in opposite direction, they will repel. Net force will be F1 minus F2 and whatever the value comes. How will you find F1? Mu naught I1 I2 L by 2 pi d. Same way mu naught I1 I2 by 2 pi d. Subtract both, you will get the net answer. This kind of question is very commonly coming in examination. Very commonly coming. Practice that question. One more thing is, from here they are asking you define 1 ampere of current. Once again, very important question. Define 1 ampere of current. So how do you define 1 ampere? I told this to you. Put here 1, put here 1, put here 1, put here 1. Then you will get the value of force as 2 into 10 power minus 7. Because V naught is 4 pi 10 power minus 7. 2 pi will make it 2 times. So 1 ampere is that current which is, when allowed to move across two current carrying conductors, produces a force of 2 into 10 power minus 7 Newton. That one definition I gave you. That definition is very important from this topic. Then comes torque on a current carrying conductor kept in a magnetic field. Again, a very important topic where derivation is very important. They ask in the examination where you have two magnets like north and south pole, and when we have a current carrying conductor kept in this current carrying conductor will experience a torque. That torque will turn it. This torque will start rotating it, and it rotates by a torque which is equal to NIBA sine theta. This is the formula of torque on a current carrying loop kept in magnetic field. N is number of turns, I is the current flowing in the loop, B is the magnetic field existing, A is the area of the loop, and remember theta. Theta is the angle made between the magnetic field and area vector. Never forget that. If this is the area and this is the magnetic field, then they are not perpendicular, they are parallel. Which are parallel? area and magnetic field, because area is perpendicular to the area, isn't it? Area vector. And this is the value of magnetic field. Are they parallel or not? Many students take theta as 90° here. They forget that this angle is not between magnetic field and area. It is the angle between magnetic field and area vector. And area vector is always perpendicular to the area. So have clarity on that. Moreover, we know that NIA is equal to M. M is what? Magnetic moment. So magnetic moment is NIA. If I replace NIA by M, then I get torque is equal to MB sine theta. Is it clear? Torque is equal to MB sine theta. This is the formula when we consider NIA as the magnetic moment. I hope it is clear to you. Based upon this, that is torque on a current carrying conductor kept in a magnetic field, we have a device called as MCG, which is moving coil galvanometer. What is that? It is a sensitive device which is used to detect the presence of current in the circuit. If there is a current coming, it will deflect and it will show you what is the direction of, not direction, what is the magnitude of current also. How it works? It works on the principle of torque on a current carrying loop kept in a magnetic field. So what happens? Whenever a loop is kept in magnetic field, there are two torques acting. First is deflecting torque. Deflecting torque is NIBA. Second is restoring torque. Restoring torque, how it is produced? It is produced because of adding a spring in the bottom. Since you added a spring in the bottom, when deflecting torque is deflecting the needle, restoring torque will once again bring it back to the original position. Because current came inside, the coil rotated, my needle will turn like this. And once again, because I have added spring below, the spring will once again bring it back to the original position. So my restoring torque, which is equal to K into theta or K into alpha, whatever I wrote in the class, you will equate both and you will get the value of alpha. And from here you will come to know that current is proportional to alpha. That is, if you have more current, we will have more deflection. When we have less current, we will have less deflection. That is what we want also. We also defined from here galvanometer constant, also called as figure of merit. In the exam, if they ask you define figure of merit, don't confuse. Figure of merit is same as galvanometer constant K by NBA, I by alpha. Okay, current per unit deflection. So that thing is very important from this topic. And then very important thing is, in MCG sometimes they may ask you how they make sure that theta is always 90°. By using what magnetic field? Radial magnetic field. Remember this word, radial magnetic field. Radial magnetic field is provided. Why? It is provided to maintain theta as 90°. Only if theta is 90°, you will have maximum torque. Okay? This kind of question is asked where they ask you what kind of magnetic field is used for that is all maintaining always theta as 90°. Second thing they may ask you how they are making the needle to come back by using spring. What spring they use? They use phosphor bronze wire spring. Why? Because phosphor bronze wire spring is having least torsion constant, and least torsion constant means best sensitivity. That makes us to come to a topic which is called as sensitivity of a galvanometer. So galvanometer has two sensitivities. One is called as current sensitivity, one is called as voltage sensitivity. And what are those? Current sensitivity means deflection per unit current, isn't it? Yes. And voltage sensitivity means deflection per unit voltage. So you will know that IS will become equal to NBA by K. Put the value of alpha here. Same way VS will become equal to NBA by KR. Generally, questions from here comes under the category of assertion and reasoning. You can expect questions to come from A and R type from this topic, where you should understand that sensitivity depends upon these four things. But increasing number of turns will also increase resistance, leading to no change in voltage sensitivity. if you're increasing the number of turns, yes, its current sensitivity will increase. But since the number of turns are becoming more wire is used, it means its resistance will also increase. If resistance is increasing, then once again, the voltage sensitivity remains same. So, next is magnetic field. Magnetic field is controlled by permanent magnets. It is not feasible to always increase the magnetic field. Area of coil increasing can lead to a bulkiness of the device, so we cannot go beyond certain area. That's why we always prefer to choose the material having the least torsion constant, that is phosphor bronze wire, which has very less torsion constant, isn't it? Then I have talked to you about how do we convert a galvanometer into ammeter or a voltmeter. So we know that how a ammeter works and how a voltmeter works. So ammeter is a device used to measure the current, and ammeter should ideally have zero resistance. So ideal ammeter should have how much resistance? Zero resistance. Same way, ideal voltmeter should have how much resistance? Infinite resistance. The question directly comes sometimes. Ideal voltmeter should have how much resistance? Infinite resistance. So you have a galvanometer and you want to reduce its resistance. The easiest way of reducing is add a very low value of resistance in parallel. Always remember, when you want to decrease resistance, you add something in parallel and something small in parallel, because we always know that in parallel connection the effective resistance is less than the least value. You have 10,000 ohm, add 1 ohm in parallel, net value will be less than 1. You had 10,000 ohm resistance, you added 1 ohm in parallel, now net resistance will become less than 1 ohm. That's how it works. And if you want to increase the resistance, add a big resistance in series. So the resistance in series will always be more than the maximum value, and in parallel it will be less than the least value. So if you want to convert galvanometer into ammeter, we connect a low resistance in parallel. If you want to convert a galvanometer into a voltmeter, then we connect high resistance in series. If you connect low resistance in parallel, then suppose current I was coming, current going here is Ig, then current going here becomes I minus Ig. Ig is the current going through galvanometer, I is the full deflection current, full scale current. So we can see that both will have same potential difference. So Ig into G will become I minus Ig into S. From here you can find shunt value, which will become equal to Ig by I minus Ig into G. This is the formula of shunt, by which you can find what is the resistance required to be added in parallel if you want to convert a galvanometer into ammeter. Same way, if you want to convert galvanometer into voltmeter, then you add high resistance in series, and for that, what is the formula we're going to use? See, what is the current entering I? So potential drop will become equal to I into G plus R, isn't it? Here I am taking G as resistance, not galvanometer constant. Here I am taking capital G as resistance of galvanometer. So here, from here I can write V by I is equal to G plus R. And from here you can write what is the value of R. R will become equal to V by I minus G. By this formula, you can find what is the resistance required to be added in series to convert a galvanometer into a voltmeter. So I have recalled everything from this chapter, right from Biot Savart law till the conversion of galvanometer into voltmeter and ammeter. Okay, Amruta, if you are able to hear me, can you unmute yourself? What happened yesterday? I heard you came to the class. Online class I kept now only, Amruta. See the group properly. I came for the class on Thursday also. I came for the class today also in the morning, 12:30.
I was not aware. I'm not seeing the group, so it was not my phone.
Anyhow, then you make some arrangements for that, because all the messages we are passing in the group only here. If you're not seeing the message in the group, then how will you attend? Because Saturday also everybody came except you. Today also everybody came except you. So you are, and yesterday when I was not, that's why I messaged in the group also that I will not be coming on Friday. I will be coming on Thursday and Saturday. But both days you missed my class. This is the online class that I've kept. That is something different. I came already yesterday and today, not yesterday, a day for yesterday and yesterday also, today also I went. Anyhow, leave that. Ivan, whatever things I gave, no, 4 things I gave. I gave important derivations, important numericals, important theory questions, and graphs and diagrams, right?
Yes, sir.
You wrote it properly?
Yes, sir.
If you are very sure you wrote properly, take a photo of it and send it to me in WhatsApp. I'll send to other people also.
Okay, sir.
Okay. In the last class, I gave from first volume what can be the important derivations, what can be important numerical questions, what can be important theory questions, and what are the diagrams and graphs to be studied. I gave to them. So I'll share with you all also. You can also go through it and prepare yourself for volume 1. Okay. We have finished volume 1. You should be strong in volume 1. Any kind of question coming from volume 1, you should be able to face it. For that, you have to practice. And whatever I have revised now, just a quick revision it is. Until you sit with questions, solve the questions, you will not understand anything. So sit with the questions now, solve the questions from this chapter. Anshul, if you have any doubt in questions, get back to me once again. I'll arrange something to clear that.
Okay, sir.
Okay. So I hope you have the past year book. Take that book and from each topic, some questions you take, solve. And when you solve questions, then you will get doubts. When you get doubts, approach me, I'll clear it. Okay. So Ivan, I'm waiting for your message. If you share it with me, I'll share with all other people also. And anything else you want to ask, please ask me, or else I'll wind off the class. Anything else anybody wants to ask? Online people? Yeah, Pratap, can you be a little louder?
One problem from Kirchhoff rule, sir.
One problem from Kirchhoff rule you want me to solve?
Yes, sir. Any simple problem.
Any simple problem you're saying? Why not? Why not tough problem, man? Why simple problem?
Anything is fine, sir.
Okay, I'll take one question now. Today only I took a question in the SSM Nagar Center also. I'll take another question now. Everybody try to solve this question. Recalling of Kirchhoff law. Good, Pratap, we'll do it. So I'll give a random question now and let us see whether you're able to solve or not. Sai Rakshana, if you're there in the class, solve it, okay? I'll ask equations from you. Yeah, don't drop before I ask questions to you. Let me give a simple question itself as asked by Mr. Pratap. Okay. So, question is like this. This also why? This is 8 ohms. This is also 8 ohms. This is 5 ohms. This is 6-volt battery. This is 4-volt battery. And you're asked to find the current flowing through each branch. Current flowing through each branch. They have not mentioned anything about the current. Just mentioned this as A, B, C, D, E, and F. Everybody, using your knowledge of Kirchhoff law, solve this question. I'll help you if you are not able to solve. Give a try. They're asking you to find the current in each branch. not given, you can choose your own direction. So I have shared in all the groups the important derivations, important numericals, everything, graphs, whatever. Go through that. Make sure to do everything before you go for the exams. I hope you are solving. If I am a student, I will take current like this I1, and from here I will take I2, and I will add both here, it will become I1 plus I2. Once again the I1 goes here and the I2 comes back. Check whether you have done the same thing or something else, that is also fine. And then I will take loops, loop A, B, C, F, A. Ideally I should take that loop, it will be more easy. Sai Rakshana, be ready. I am taking loop F, C, B, A, F. Unmute yourself. Leave now. You see the tell once again for my loop. See the board and tell me. F, C, B, A, F. In this loop, go step by step. Tell what is the equation. Fast.
8 into I1 plus I2.
Very good. Going correct, Sai Rakshana. Proceed.
Plus
Yes.
8.
Yes.
8 I1
8I1. Very good.
equal to 4.
Very good. You are correct. If you have got the same equation, you are going in the correct direction. Okay, next loop. Amruta Varshini. If you are there, Amruta Varshini, will you try? Are you there or you dropped? Yeah, you are there. Okay, try. Loop F, C, D, E, F. Give a try.
8 I1 plus I2
Yes.
plus 8 I2
How 8 I2? This is 5.
to this side.
So plus 5 I2 equals, you are correct. Good. Since we have only two unknowns, it is sufficient. We have two unknowns, we have two equations. If you are solving these two equations, you will be definitely getting the answer correctly. After that, make these two equations and just find the value of I1 and I2. Pratap, did you do the same way or something else you are doing?
Same way, sir.
Okay, did you
Solving the equations.
get the value of I1 and I2?
Doing, sir.
Okay, make it fast.
Nearly.
Yeah. 16 I1 plus 8 I2 is equal to 4. Here you will have 8 plus 5, 13 I2 plus 8 I1 is equal to 6. So here I can take 2 outside, then it will become 8 I1 plus 4 I2 is equal to 2. I am doing it intentionally because both are 8, 8. I'll subtract both. Then 13 minus 4 will become 9. 9 I2 will become 4. I am getting I2 as 4 by 9 amperes. Anybody supporting me?
Yes,
Sir, I got
I
4
know
by
that, sir.
Okay, so you got same 4 by 9?
Yes, sir.
Then you are fine. Yeah, either I am wrong or we all are right. Okay, anyhow. I2 we can easily find I1 now. Put in any equation, get the value of I1. Okay. So I hope you understand. Main thing is equation forming. After equation forming is basic mathematics. That I think everybody should know. If you're not knowing, it is bad. And then this is what Kirchhoff law is. Anything else anybody wants to ask? I don't have much time now because there is another class going to start at 6 o'clock in the studio. So I have to wind off the class. If anything else is okay, if anything else anybody has to ask something with me, WhatsApp me, call me, we will arrange something for that. Okay. So I have shared the important things in the group already. Please go through that. If you have any upcoming examinations, start preparing for it. It has everything I told you. It has derivations, it has numericals, it has important graphs and diagrams, it has important theory questions, from where theory questions will come. Everything I have given. If you are strong in all these things, then in school you can get good marks. Okay. So I'm winding off. We will meet.
Was that class recorded, sir?
This class that is happening now?
Not this, sir. That class which one?
No, it was not recorded. That's why I shared the written part to you. If you feel handwriting is not that good, then you can come back to me. I'll help you with what is written. That is Ivan's problem. Anyhow, if you have problem in understanding how he has written, then I can ask Sai Rakshana, did you write neatly? Somewhat means it will be bad only. Anyhow, you also share with me. If I feel your things are little better written, I'll share your things also in the group. Because anyhow, anybody has to ask something, please ask me in WhatsApp now. I'm dropping off. Bye bye. Take care.